And welcome back to thermodynamics. Today we are going to be looking at thermal efficiency, the second law of thermo, and the Carnot engine. So first of all, what is thermal efficiency? Thermal efficiency is how we measure and compare the value of a cycle. And we use the symbol eta. Now, eta is like an N with a tail. And in thermodynamics, the way we talk about how good something is what we get out, the value out, divided by the cost. And we do these in terms of energy. Well, the value out of a Rankine cycle is the work of the turbine. However, it's not just the work of the turbine. So let's say that we got 800 BTUs per pound of specific work out of our turbine. We can't sell all of that. And the reason we can't sell all of it is because some of that work needs to come back in and run the pump. And these are usually really small. Like in an example we just saw, it was 6 BTUs per pound mass. So it's still a good thing. We still get to sell a whole bunch of our work, but we have to take off that little bit that we need to run the system. So the value out is the net work, or the work of the turbine minus the work of the pump. What does it cost? What's the one thing that we pay for in a Rankine cycle? No, we pay for the coal. We pay for the heat transfer in. So there it is. The thermal efficiency of a Rankine cycle is the net work divided by the heat transfer in. A typical value for a simple cycle like this with no other pieces and parts to make it more efficient, 25%. That sounds horrible. Kind of is. But it's really the price we pay, because I can't plug my iPhone into a piece of coal. Now, fortunately, the power plants can sell 1 BTU per pound mass of electricity for a whole lot more than they pay for 1 BTU per pound mass of coal. But for each 4 that would come in, only 1 is useful work. The rest of it gets thrown away here in the condenser, and that just doesn't seem right. Take an advanced Rankine cycle, and we can analyze that. Now, out at Minnesota Power, one of our partners, they have many more little processes in here that cause this number to go up to 50 to 60%. We have 4 H's in all of the work we've done in core thermo. In advanced thermo, we would end up with 28, 29, 30 H's. to bring in all of those other systems that cause the thermal efficiency to go up. This is all good. It's great. Well, it's kind of great, but we're still only at 50 to 60%. What a horrible thing that is. All right, thermal efficiency. Check. Now we're going to talk about the second law of thermo. And the reason that I'm doing it in this video is these are very, very, very much related. The second law of thermo has like 3 different corollary statements. But what it all comes down to is that the second law says the thermal efficiency cannot equal or be greater than 100%. The second law says we can't be greater than 100% and we can't equal 100%. It's the second law of thermo that is the reason you can't have a perpetual motion machine. A perpetual motion machine theoretically could be okay with the first law, the law of conservation of energy. But it can't be greater than, it can't even equal 100%. The first law would allow you to equal 100%. The second law says, nope, you can't even get there. So I'm going to put a great big can't happen. Now, one of the ways that the second law is stated is it says you cannot accept and reject heat to one temperature source. Accept heat from and reject heat to one temperature source. So let's take a look at that. We're pretty familiar by this point in the game with the temperature entropy diagram. And this is the high pressure and this is the low pressure. And they would each have a temperature associated with those. So let's just call them temperature high and temperature low. Well, from our work with air conditioning cycles, we know that this temperature high is the temperature of the water when it's getting heat transferred into it. So what we know is that the temperature of the fire must be somewhere above that. And we know that the temperature low is where we are rejecting heat, doing heat transfer out, and we know that the temperature of the cooling water must be below that. For us to transfer heat into the working fluid and out of the working fluid, we must get it from a high temperature and send it to a low temperature. Well, what the second law says is you can't bring these two together. They can't be the same thing. Because if I had just one temperature, let's call it single source, how would I get heat from it and reject heat to it? It would shrink this down to one line. There would be no heat transfer in, there would be no heat transfer out, and with no heat transfer in and no heat transfer out, I can't get any work. Yet, to achieve 100%, I would have to be at a single source. So, it just can't be done. I encourage you, if this interests you, to look in our book and read the different corollaries of the second law. Look them up online. But really what they come down to is that you can't even achieve 100%. Part 2. Now, part 3 is the Carnot Cycle. Carnot engine, Carnot cycle. And here's the deal with the Carnot engine. It is going to tell us what is the maximum thermal efficiency without violating the second law. Carnot cycle allows us to find the maximum thermal efficiency without violating the second law. So I'm going to redraw that temperature entropy diagram. And I'm going to start with the temperature of the fire. We call it the temperature of the source, the heat source, temperature of the fire. And the temperature of the cooling water, we call that the temperature of the heat sink. It's the place where energy gets rejected to. Temperature of the cooling water. Now, I wonder what the temperature is when you burn coal. What is the combustion temperature of coal?
Let me check on that. Here's what I found on the web for the combustion temperature of coal.
I'm getting answers anywhere around 2,000 degrees Fahrenheit. So let's say 2,000 Fahrenheit. And the temperature of the sink is usually the temperature of the river on a given day. Water, well, at plant 1 and 2 in Cohasset, they use the river water. Plants 3 and 4, they use a cooling water system. But let's just say that it's 60 degrees Fahrenheit. On hot days, that's going to be less. Excuse me. On hot days, that's going to be more. So now I'm gonna make my Rankine cycle, and as we talked about a few minutes ago, the temperature of the cooling water has to be below 2,000 when you transfer heat in. But what we're going to pretend is, what if we could go all the way up to 2,000? That's going to give us the maximum heat transfer in. And we know that our temperature has to be above 60, but we're going to bring it all the way down to 60. And we're going to let our work processes be ideal. So this Carnot cycle allows this box to be as big as possible. Well, we know from the first law, let's see if I can get a little more space here, that for the whole cycle, the net work, W dot of the turbine minus W of the pumps, is equal to the net heat transfer, Q of the boiler minus Q of the condenser. Well, this box right here equals Q of the boiler, area under the boiling, minus Q of the condenser, area under the condenser. So the difference between those is biggest when I bring these temperatures all the way up to 2,000 and all the way down to 60. I can't make this box any bigger, because if I go above 2,000, I'm not going to get heat from the fire anymore. I'm going to give heat to it. That doesn't make sense. I'm not going to give heat if I come down further. I'm not going to give heat to the cooling water. I'm going to get heat from it. Oh, that doesn't make any sense. So the biggest we can make this box, the biggest we can get the net heat transfer, which means the biggest we can get the net work, is when we go to the temperature of the fire and the temperature of the sink. We can't achieve that in the real world, but theoretically, that's as big as we could go. Frictionless processes, we can't achieve that either, but theoretically we could. So let's go a step further and say, well, what would the efficiency be of this? What would the efficiency be? Well, it's a nice derivation, and if you take advanced Rankine, we'll do it. But it really does simplify. It turns out that it simplifies all the way down to the temperature of the fire minus the temperature of the cooling water over the temperature of the fire. And it does that in, you have to be in absolute temperature, kind of like the ideal gas law. So we have to get into Rankine. So 2,000 plus 460 is 2460. Minus 60 plus 460 is 520 over 2460. Grab my fancy little calculator here. $24.60 minus 520 divided by $24.60, 78%. Closer to 79%. So that's a Carnot engine. That's the Carnot cycle. Can't build it, but it doesn't violate the second law. So why do we care? Well, let's say that you're working for a power plant, and you're working at the power plant, and it turns out that your boss is a business major and not an engineer. And the boss says, hey, your plant is only operating at a thermal efficiency of 60%. That's a reasonable, real thermal efficiency. Which, you know, that's better than the thermal efficiency of a plant that only would have a boiler and a condenser and a turbine and a pump. So you think you're doing pretty well. And your boss says, well, I want to be closer to 100. I want you to get this to 99% efficiency. And, well, you know, remember what the second law told us. The second law says we must be less than 100. So you can't throw that at your boss and say, hey, the second law of thermodynamics, by the laws of physics, prevents us from getting to 100. And he's like, okay, no problem. Let's go to 99. And you're like, huh, can't do it. Why can't we? Because the Carnot efficiency is equal to 79%. And what the Carnot efficiency gives us is the opportunity to have a comparison of what the best is and still obeying the second law. So this is the best obeying the second law. But we can't get there. We can't have frictionless work processes. That's not real. We can't transfer heat from 2000 degrees to 2000 degrees. It doesn't transfer that way. So we need to have bigger temperature differences for our heat transfer. And so what you can do is you can go to your boss and you can tell her, well, we're at 60%. The laws of physics prevent us from going above 79%. And here are all the reasons why we can't even get to that efficiency. So the Carnot efficiency is a thing. It's the highest efficiency that doesn't break the second law. It has only to do with temperatures. And all of these are comparison factors that when you are an engineer at a power plant, you need to know. You need to know why you have all those other processes that get you from simple to complex. And along the way, you would calculate all of those efficiencies. All right, so what is the takeaway for core thermo? Second law prevents us from getting to 100% efficiency. That's one takeaway. Another is, what is thermal efficiency? I'm going to need to be able to describe that. And then the third takeaway is that there's this thing called the Carnot efficiency that is the best efficiency you can get to without violating the second law. All right. Later, Gator. That's funny because there's somebody in this class, the year that I'm recording this, named Gator.